Hey there, my name is Gary Sims and this is Gary Explains. Now, if you've been following my series of videos about how CPUs work, remember we've got to the point where we defined our own CPU instruction set. We've built the tools and assembler and disassembler to use that instruction set, and finally we've learned how to emulate that processor using a Raspberry Pi Pico, because it's a small microcontroller, and then it can now read the machine code for that processor that we've defined. Now the next step is to actually use that Pico as a discrete component, so in replace of a CPU, and maybe we can talk to some RAM, we can talk to some I/O, we can talk to some ROM. Now before we do any of that, we need a clock, and we need to have a clock module that sends a pulse at a certain frequency, 1 Hertz, 1 megahertz, whatever. Now there's a great video, a series of videos by Ben Eater here on YouTube, and I highly recommend them. And I absolutely admit that a lot of the inspiration that I'm about to show you for this Raspberry Pi Pico version comes from all the work that Ben Eater has done. Absolutely go and watch it. Absolutely fantastic set of videos. Now what we're going to look at today is how we build a clock module that we can generate a clock signal for a computer circuit using a Raspberry Pi Pico with the ability to stop the clock, step through a certain number of pulses, start the clock again, and so on. So if you want to find out more, please let me explain. Okay, so let's start by looking at the actual hardware that I've made for this. So obviously here is a Raspberry Pi Pico. As you can see, not very much needs to be attached to it. Start up here in the top right hand corner, what we've got, that's the ground pin. If you look here at the layout, that's pin number 3 there, that's ground, well pin 38 I suppose it's technically, pin number 3 on the right hand side. And then you go down to, and then you've got 3.3 volts out, which is that. So basically now these two rails have got ground and voltage on them. And then of course the most important thing here is the buttons, because we want to be able to control this clock. We want to be able to set it so it just goes at an automatic rate. We want to be able to step through it. So 2 buttons, one of them here is connected to this pin here, which when you look on the pin out is GPIO number 10, and then this other button is connected to the bottom one here, so that's GPIO number 15, and on the other side of the button they both go through to the positive rail. So when the button is pressed, it basically makes a connection through to the positive, which means that pin goes high. So in the software we can check to see whether the pin is high, that means the button is pressed, and that's the same for both of them. Checking GPIO 10 for one button, GPIO 15 for the other. And the final thing on here is just an LED, and then of course a resistor that you need. So that basically is the clock, and what we will do when you use it is you take an actual fly lead here and we plug that into the same output there. That's the very last GPIO, that's GPIO 16, and now this has got a clock pulse on it, and we can then plug that into another circuit board. I will demonstrate that at the end of this video. But the next thing we do look at now is the software that I've got running on this to see how that works. Okay, so here we are inside of the code. It's written in MicroPython. Really is quite simple if you break it down into its component parts. What is it in total? 50 lines of code, so it's not particularly hard. So what we've got here at the start is we define those 3 pins. The clock itself is of course an output, that's why we've got the word out there, and then we've got these 2 inputs which are for the 2 buttons, pin 50, GPIO 15, GPIO 10 as we discussed. One is called the mono stable trigger and is the A stable. So basically a way of turning it on and off, and the way to step through it one step at a time. So we have a timer which we're going to use later on for doing that clock pulsing, and we're going to talk a bit about a thing called double bounces in a minute, and so we need to know when something last happened, and that's just measuring the time there in milliseconds, so we'll worry about that a little later. And then there's basically an A stable, true, false, that just tells you whether it's in that constant clock just automatically going or whether you're stepping through it. Okay, we'll skip down to the bottom. Basically what you do is that you create a timer, okay, and it calls back this thing called clock callback, which is this function here, and all that does is just toggle. So if it was on, it goes off. If it was off, it goes on. So really simple. And this is going to run at a frequency of 1 Hertz. Now you've got 2 in here because why? Because inside every hertz you need to go high and low for an equal amount of time. So half the time you're high, half the time you're low. So you actually want to run the clock twice as fast as you actually want your output clock to be, so that this toggles twice. So in times of 1 hertz, you actually get high, low, and then back to high again. So remember, if you want 1 hertz, go to 2. If you wanted 8 hertz, this needs to go to 16, and so on. And basically that will just run now. If you fire that off, it will just run, and then the clock will just start at that frequency. So when you want to change the frequency, you can go into there and set it to whatever you want. Now, while that's running, Python will drop into this while loop, because this timer happens in the background, because it's a timer event, which then calls a callback. So it actually falls into this permanent loop, this infinite loop. It just goes round and round and round. And what it does, it calls this function, which we'll look at in a minute, called wait pin change for monostable trigger. So that is pin 15. So what it's basically saying is it's waiting for that bottom button to be pressed, and it's waiting for it to change. So it's off by default. When it becomes on, then it actually triggers this. And it basically, if we're not in the astable state, so we're not relying on this timer going round and round, then toggle. So that's the idea, is that by pressing the button and then releasing it, we get a whole clock cycle. It switches it on, and then of course it will wait for the pin to change. It will change now from on to off again, so we'll toggle it again. So the longer, as we press it, it goes high, and then when we let go, it goes low, and it will just sit in this loop. Now if it's in the astable mode, then it won't do anything. It will just skip. Doesn't matter how much you press that button, it will just sit in there and wait. So what does wait for pin change do? Well, that's up here. Now basically, with a button, because it's physically you're pressing it, you can, from an electrical contact point of view, have a thing called a double bounce. So basically that means is, as you're pressing it, the contact kind of makes an initial connection, and then we're talking fractions of a second, it goes off and goes on again, because it's a mechanical pressing, and that can kind of cause a blip rather than a nice smooth thing. So what you want to do is, when you go in here, you want to see whether at least that has been a continuous connection for 50 milliseconds. Not very long in terms of a human, a long time in terms of a microcontroller. And basically this while loop basically says, okay, I will just wait until I know that this has been pressed consecutively for 50 milliseconds, and then it will return, because it returns when it has changed, because it's wait for the pin to change, and it will no longer wait when the pin has changed. If it is 0, if it's a double bounce, this counter gets set back to 0, and it waits again until another 50 milliseconds is complete. Each time it's sleeping there for 1 millisecond, and that takes away the double bounce. So not enough that you can do it fast enough with your finger if you want to tap through quickly, but enough for just that slight problem of it not connecting as it should do, and you don't want to get a double click, as it were, for actually when you're only intending to press it once. So wait for pin to change will go around this loop until it sees that the value has changed for 50 milliseconds, and it will exit. And then of course, because it's exit, it then goes around, does this next thing, and then the pin will then be high, and it will wait again until you let go, and that's the way that works. So that's all pretty simple. Now there's just one other thing, and that is that we've also defined here on an IRQ a trigger for the astable monostable button. Astable monostable, the switch between the automatic clock and the clock that you're pulsing your way through, and that basically says call this button handler here when you see that the button's been pressed. So same thing, when an IRQ will fire, so you don't have to monitor it in this while loop, it's an IRQ. So it's great here, we've got two things that are going on automatically, IRQ and a timer. They both go on in the background, waiting for an event to happen, waiting for something to happen, and then the respective code is called at the right time. So this basically says, when this happens, then call this button handler. And what does this do? Well, it imports a whole load of stuff that it needs to fiddle with, so all those globals, that's because all these things are defined up here. And then what it basically says is, if it's been more than 500 milliseconds since the last time the button was pressed, again, so we don't want to get double clicks going on here, then it says if we're in astable mode, then go to non-astable mode, turn off the clock, deactivate the timer, okay, and then just set that last time clicked again now to the current time, so that we don't get, if it then does leap around here again, if the IRQ is called again, it just ignores it. It says no, I've been in here recently, I'm just ignoring all this stuff. Now if it's the other way around, if we're not in the astable mode, then it turns the astable mode back on, reinitializes the timer, which is actually the same code as we had down here, reinitializes the timer, and again sets that last time seen thing, so we don't get any double clicks. So basically pretty simple. If we're in one mode, turn it off, turn off the clock, turn off the LED. If you're in the other mode, turn it on, re-establish the timer. As simple as that, and this gets called automatically. So between these two, we can switch between the A-stable mode, which is tested here using the top button connected to GPIO 10, and we can step through it using the other one on GPIO 15. Simple as that. This code, of course, will be in my GitHub repository. Okay, so let's do a quick demo. Now, I apologize, this is quite crowded and I'll try to do better when we actually come on to future videos. But basically what you need to know is that here is a 6502 processor, and here is a Raspberry Pi that I'm communicating to that. And one of the things I want to do is to be able to emulate an EEPROM using a Raspberry Pi Pico. Rather than having an EEPROM and an EEPROM eraser and an EEPROM programmer and all that kind of stuff, we can just do it with a Raspberry Pi Pico. But what I wanted to show is that here we have our clock module, and then that lead, if you follow it, goes all the way through over to here to the clock pin on the 6502. And then another pin up here is actually the output of that. So the 6502 has actually got an output and an inverse output, and that then comes down here to this LED here. So while we're not looking at anything, the 6502 is actually running specifically, what we are showing is as the clock pulse is coming in through there, it's actually coming on an output of the 6502 and giving us that output there. So it shows that the clock is being received and is being output again. In fact, what we can do is we can move that pin over to the inverse output, which is over here. And if we just touch on that leg there, now you can see, if I can keep it steady, there we go, is the inverse output. So when it flashes on this side, it's off on that side. When it's off on that side, it's flashing on this side. And again, that's showing that the clock is going into the 6502 and then coming out again. So there we go. That's a demo of the kind of thing we need to do. And of course, as I've said, you can step through on this. If we turn off the automatic clock, we've now stopped it. And then we can use this one to pulse through, so you can follow exactly what the 6502 or any other chip that you want to test against is doing per clock cycle. Okay, so there we have it. There is my clock module, and as I said, absolutely inspired by the work that Ben Eater has done. Do go and watch his videos. I'm kind of not really a hardware person, I'm a software person. My education is in software, but you know, you have to tinker with hardware, you have to play with it a little bit, and so really this is taking a full hardware version of a clock like Ben Eater makes and now making kind of a software version using a Raspberry Pi Pico, and then we can build up these blocks. As you saw in the demo there, I've got a 6502 up and running, and I want to kind of build a circuit using Raspberry Pi Picos rather than other discrete integrated circuits, other discrete chips, and ultimately I'll replace that 6502. Maybe that's a bit of a bold promise. We'll see, and replace it with a Pico emulating a 6502. Well, let's see if I actually get to that stage. Okay, well, I really hope you enjoyed this video, and I hope you enjoyed this series of videos. If you enjoyed this video, please do give it a thumbs up. If you like this series, make sure you're subscribed to the channel by hitting that subscribe button. Don't forget you can follow me on Twitter at Gary Explains, and I also have a monthly newsletter. Go over to GaryExplains.com, type in your email address, no spam, but you will get the email newsletter. Okay, that's it. I'll see you in the next one.